So in this video lecture, we're going to talk about how to add a driving dyad to an existing mechanism. So you'll see that on the top of this screen, I have a 4-bar mechanism. Let's say that I want to add another pair of links that drive this through its range of motion. That's our task here with the driving dyad. We're going to synthesize this graphically, and this becomes very useful to create really the simplest 6-bar mechanism that will drive a 4-bar. So our task at hand here is an oil well pump. This is a little bit unique design in terms of comparing it to the existing crosshead designs that you normally see out in the oil fields, but the objective of this 4-bar linkage is to create a relatively straight line motion of this coupler point right here. So this moves in a relatively straight line up and down, and therefore is moving the moving element of the pump that's down there in the oil well. And I've got this 4-bar mechanism. I've got a ground pivot here as well as a ground pivot here. I've got links going out to B1, my coupler link going out to the precision point, and then a link going back from A1 to the other ground pivot. So let me impose that 4-bar mechanism on top of there, and now you can see a little bit better as to what's going on with this 4-bar. What I want to do with this now is say, I've got this 4-bar that gives me a relatively straight line motion that I want, but I want to be able to drive this with an electric motor. The electric motor is making continuous revolutions, and none of these links make continuous revolutions. So I need to add this driving dyad. The other thing I want to do is I want to spend the majority of my stroke in the pumping stroke and then have a quick return, which means that I'm basically going to move it down very fast because I'm not going to be doing any useful work during that part of the stroke. So I'll set up a timing ratio of the time for the upstroke versus the return stroke. That's my objective. So let me take this 4-bar, extract it from this picture now, and blow it up a little bit so that I can start to do my synthesis. Now, first of all, I'm going to draw a line from A0 to A1, and that is going to be the link that I will be connecting my driving dyad. So in other words, I want to have another pair of links that drive into that input link, or drive into that A0 to A1 link, and push it through its range of motion. So my range of motion here from A0 to A1 when it swings through its let me get another laser pointer. This would then be the position A2, or perhaps, this is the end of motion from A1 position down to that position right there. So what I'm going to do now is start to go through a procedure for outline, that outline my process for this driving dyad. I'm going to first of all pick some location on this link A0 to A1, and I'm going to call that my moving pivot C1. Now, I've happened to pick it along the line from A0 to A1, but I could make this link an odd shape and connect it somewhere else. Realize that this is just an arbitrary convenience that I've done to make the sketch that I'm going to create a little bit easier, but I really could have picked it anywhere else. So I've got C1 here, and I know that C1 is going to swing through an arc and go to a C2 position. Again, still attached to that link A0 to A1. So it'll go to that C1 to C2 position. All right, next thing I'm going to do is pick a timing ratio for this mechanism. And this will define this angle alpha that we're going to use in a second. So the idea of this timing ratio, as I mentioned previously, this is the time for the advanced stroke compared to the return stroke. So in this case, I happen to have picked an alpha angle of alpha is equal to 15 degrees. And by doing so, my timing ratio, if I plug in these numbers here, ends up being, I believe it's 1.18. So this basically means that I'm spending more of my stroke on the advance than I am on the return. So again, allows me to have more of the time spent during the pumping operation versus the return operation. Now, once I've defined this alpha angle I'll be using in just a moment, and what I'm going to do is try to find where is the ground pivot of my motor going to be located. So this we'll call C0. And the way I find this is I draw an arbitrary arc right here. And this is from the C1 location, and this is a choice that I get to make as a designer as to where this arc is going, what angle this is at. You're going to find that if I picked a different angle, I'm going to get a different solution, and there's a whole infinite number of solutions that I could create by having different angles here. So I happen to have picked this angle for this line that I've drawn, this ray. Now, that alpha angle I told you about a moment ago, this is where we're going to use it. This 15 degrees is going to define the location of that C0 ground pivot, and this angle is from C1 to C0 back to C2. So that's my 15 degree angle that I specified a moment ago. and that intersection of those, or the base of that arc, that is my C0, or the ground pivot of the motor that's going to be continuously revolving. Next thing I need to do is figure out how large is the radius of the crank on the motor. The way I do this is I say, all right, the distance from C0 to C1, and I compare that to the distance from the C0 to C2. And you can see that what I've done here is I've taken this C0 location and I've swung an arc about C0. So I've swung this arc and brought it over to a line that's right along C2. And then I've measured this distance, which is 2r, from C2 up to that arc. That 2r right there is going to be the radius of the crank, or 2 times the radius. That'll be the diameter of the crank that I'm going to have rotating about C0. So this distance 2r, r is the radius of this, 2r is the diameter of that crank. Now I have enough information to synthesize the remainder of the mechanism and sketch the driving dyad. So my driving dyad, I'm going to again have this be the ground pivot of my motor. This is the moving pivot of that motor, so in other words the crank is this piece that revolves around that green circle. And then I'll be connecting the rest of that with a link out to that blue link. So this link right here is the connecting link out to this blue link, and we have created now a Watt-2 mechanism, a 6-bar mechanism, and as this point revolves around here, we're going to see that we move this mechanism back and forth from C1 to C2. The other interesting thing is that you can imagine this point right here, right now when we're collinear between our crank and this connecting link, we're at the farthest extent that we would get to. As I revolve this around, and now I'm on the line that moves out to C2, that would be the farthest retracted that our mechanism would be. So the angle right here, this alpha that we use to prescribe, that is where the timing ratio comes in, and that I'm going from here to here to move from C1 to C2, but then as I go from C2 back to C1, I move through a larger piece of the arc, 15 degrees plus 180 versus 180 minus 15. So that's what gives me the timing ratio for this mechanism. And again, I can take off my sketch lines, and now I have my complete 6-bar mechanism that I started with my base 4-bar, I added this driving dyad. And we're going to find that regardless of how we synthesize that base 4-bar, we can always add this driving dyad, and this graphical approach is a pretty quick, simple way to do it, where we still pay attention to this timing ratio, or the percent of time that we're in the advanced stroke compared to the return stroke. So pretty powerful, and the extra degree of freedom that we have in these free choices, we got to pick where our C1 pivot is located. We also got to pick what the angle was of this ray that went from C1 out to C0, and then that is where we define the 15 degrees from. So quite a few free choices that you got to make as a designer here.